Hello, my name is Ashraf Gaikwad. I am from SS College of Engineering. We are all final years of Mechanical Engineering Department. This is Vamshi Rama, this is R. Dinesh, and this is Suraj.
Yeah. Hello all. Today I will be explaining through the experimental model analysis. Myself is Srinidhi Acharya SA from the Department of Mechanical Engineering at SS College of Engineering. I am working as an assistant professor over here, and I am also the PhD research scholar at this institution. So even my PhD work is based on this experimental analysis. So here what you can see on this platform, it consists of model analysis experimental setup. So from scratch, if you want to start means, so this is what we call it as 8-channel DAQ system. It is called as 8-channel. Why the reason? Because we can see 8 channels are there where you can plugins with the many cables over here. So one end of the connection is given to the display system. Display system, that is what we call as the computer system, and one is the power supply. So as of now we are using the first 2 channels. Either we can take from this end or the other end, it doesn't matter. So we are using 2 channels over here. So the first channel, what we can see, it is connected to the one more component called as the excitation hammer, or also called as the impact hammer. So this is the impact hammer. The second channel is connected to the one more parameter, so that is called as the accelerometer, the highly sensitive component over here. This is the accelerometer. Yes, in the video you can see few more accelerometer. So these are the various types of accelerometer. This is also called as a force sensor. So this is for the higher capacity, and one is for the triaxial acceleration measurement. What we can see here is the x-axis, y-axis and the z-axis indication of triaxial accelerometer sensors. So these are one of the most sensitive parameters in the whole experimental setup. And here what we can see here is the frame. It is the model frame where the major analysis are done. So in the meanwhile, in the video we will be just showing you how to conduct the model experiment. And coming back to here is the display system. So display system is nothing but the computer system. So the software for this one is the Dewesoft model analysis software. So this is the full version of the Dewesoft what we have installed here. So this is the interface of the analysis software. This is the interface of the analysis software. So how to proceed with the analysis, how to go ahead with the model analysis will be shown by the step-by-step procedure. So meanwhile, coming back to the connection, so these cables are called as the bungee cables. Clear? So as I told you, one bungee cable is connected to the impact hammer and the other is connected to the accelerometer sensor. So on this model frame, we can conduct a number of analysis, like for a different boundary conditions. The boundary conditions may be fixed free, which acts as a cantilever, or a free, or both end fixed. So as we are moving for the experimental model analysis, we have selected one aluminium component. You can see in the video very clearly over here. So it is acting as the fixed free. How this is calibrated, how this is fabricated, so that will be shown over here. Here is the list of aluminium samples. So it is aluminium 7075. Why we have selected aluminium 7075? Aluminium 7000 series, as we know, it is majorly applicable for aircraft or aerospace industries. So we have taken aluminium 7075 with a list with a various amount of reinforcement. The reinforcement what we have selected here is the titanium carbide and the silicon carbide. So you can see here n number of components are fabricated. The fabrication is done by the help of stir casting techniques. So almost 25 different set of specimens are casted over here. So silicon carbide and the titanium carbide are heated above its melting point temperature in a graphite crucible, and the specimens are casted. Now one specimen we will just show you. So this is casted as per the ASTM standards. So this is what you can see here is the 8% of silicon carbide with the 4% of titanium carbide and the 7075 aluminum. This is divided into n number of equal components. We are just drawing the horizontal and the vertical line. The intersection of horizontal and the vertical line is called as the nodes like node 1, 2, 3, 4, 5, 6, 7, 8 that goes on up to 30 in for this specimen. So we have divided equally. So with the help of a C clamp, first we are going for the first specimen what we have taken. So we are conducting analysis for aluminum 7075 with the 2% of silicon carbide. So we have designated the code as 2 for our reference. So what we can see, as I told you, it is divided into n number of parts, that is up to 30 nodes. So it is kept on the platform on this frame over here, and you can see one of my students is just clamping the one surface using a C clamp. So eventually it acts as the fixed support. So one side is fixed. The other end is left free. So eventually what happens, it's now acting as the cantilever beam. So for the full protection, so at the bottom of the frame we have just covered with a mat with a good thickness, and we have just even kept some bubble wraps so that suppose if it is falling down that should not hamper the virtual components. So during the course of time, during the experimentation, what happens? So what we are having here, the accelerometer. So now we are conducting the uniaxial test. If I want to go for triaxial means, I will just go with a different accelerometer. So this is the accelerometer. As I told you, this is one of the sensitive parameter over here. So the accelerometer, it is applied with the petroleum wax. So this is the petroleum applied with the petroleum wax or a beeswax. So it is applied, this acts as a glue and it will not hamper the vibration. So this is generally connected at the last node, to the bottom of the last node.
Well, new setup. First one we'll name it as hammer, and second one we'll name it as accelerometer. And we'll change the physical quantity of hammer to force, and accelerometer physical quantity will be acceleration. And now next we'll go to more. Okay, so before that we'll have to change the bandwidth to 5000, and now we'll go for more, and then model test. Test method will be impact hammer. We'll take the roving hammer and we'll keep the resolution to DF. Averaging type will be linear, and we'll stop after 4. We'll be using ordinary mode indicator function. The pre-trigger will be 1 and the trigger level will be 3. Second hit level, force plus exponential. We'll be selecting the window for force plus exponential. The window length will be 10% and the window decay will be 10%. Okay, so we'll be having total of 30 nodes, and for each node we'll be giving 30 excitation points, excitation inputs, and from those 4 excitation inputs we'll be taking, the system will be taking 1 excitation channel. So we'll be having a total of 30 excitation channels. Okay, so we'll be having total 30 excitation channels. We'll name the input of all the 30 excitation channels as hammer, and the units must be N, and the physical quantity must be force. Now to the response. We'll be having just one response, and that will be accelerometer, and the physical quantity will be acceleration, and the units will be meter per second square. Now we'll go for measure, and from measure we'll be going to empty impact hammer. Click on this area, and then we'll have to go for edit. After you are done with frequency, we'll have to click on store, click overwrite. Okay. Now we'll be having total of 30 nodes, and for each node we'll be giving four excitation inputs, and after four excitation inputs we'll be clicking on next excitation point. First excitation point, second, third, fourth, and now next excitation point, second, third, fourth, and next excitation point, second, third, fourth,